Okay, class, now that we've talked about how to set up and solve a basic stoichiometry problem, including either a mole-to-mole conversion simply, or a more complex problem going from grams of one substance to grams of another substance by doing a molar mass conversion, then a mole-to-mole conversion, and then another molar mass conversion. We're going to use these techniques and we're going to expand into a little bit more complex problem called a limiting reactant problem. So I mentioned the phrase limiting reactant before. Fundamentally, a limiting reactant is when you have two or more reactants and you don't have enough of one of the reactants to completely react with the other reactant. So it says sometimes a chemical reaction is conducted in which there is not enough of one of the reactants to completely react all of the other reactant present. And this therefore limits the amount of product that can be generated. So when a reactant limits the amount of product that can be produced, it is the limiting reactant. And to determine if there's a limiting reactant that is limiting our product, we must calculate the amount of product that would be theoretically generated by each reactant separately, given the amount present. And we call these calculations limiting reactant calculations. And I abbreviate them LRC. So a limiting reactant calculation is basically just a stoichiometry setup, just like this. Only you're going to run it based on starting with each individual reactant to see how much product each of those reactants can give you. And then that will tell us which one will limit the amount of product I can get. So before we do that math, I just want to make sure that we're grasping the basic concept here. We have all used limiting reactant calculations in our lives. This is not a new concept for us. We are all familiar with doing these basic sort of calculations in our heads. So here's a sample problem that is not working with a chemical reaction. Imagine you're making some cheese sandwiches. So you have a loaf of bread and there are 16 slices in the loaf, and you have 5 slices of cheese. And you know that to make one sandwich, you need to use 2 slices of bread and 1 slice of cheese for each sandwich. So how many sandwiches can you make? Well, we need a balanced chemical reaction, or a balanced equation in this case. So I'm going to write that symbolically. So I need to have 2 slices of bread and 1 slice of cheese to make one sandwich. So I could write that symbolically to say 2 slices of bread plus 1 slice of cheese can be brought together to create one sandwich. Okay, 2 slices of bread and 1 slice of cheese are needed to create one sandwich. All right, now that I've done that, I need to figure out how many sandwiches I can make. How many delicious sandwiches can you make? And fundamentally what we have to do is we have to figure out how many sandwiches could be made out of 16 slices of bread and how many sandwiches can be made out of 5 slices of cheese. So I'm going to put those numbers right under there. So how many sandwiches could I make out of 16 slices of bread? Well, it's a 2-to-1 ratio. So if I think about this in my head, well, I could make 8 sandwiches just based on the bread. How many sandwiches could I make out of the 5 slices of cheese? Well, it's a 1-to-1 ratio. So I could make 5 sandwiches just based on the cheese. Well, if I could make 8 sandwiches out of my bread, but only 5 sandwiches out of the cheese, then obviously it's the cheese that is limiting how many sandwiches I can make. So the cheese is my limiting reactant. So that's what we mean by limiting reactant. It is the reactant that is going to limit the amount of product that I can make. Now, we do this kind of math in our head, but we could do it formally in a dimensional analysis. And so that's what I'm going to do. I'm going to do LRC number 1, my limiting reactant calculation number 1. I'm going to start with 16 slices of bread. And I'm going to say, okay, I need a conversion factor. 2 slices of bread for every 1 sandwich. And then I figure out that I can make 8 sandwiches based on the amount of bread I had. If we do the same thing from the cheese, I can say I have 5 slices of cheese times, and here the conversion factor is going to be for every 1 sandwich is 1 slice of cheese. And you can see that my answer here is that I'm going to get 5 sandwiches. And there's my answer. So based on the bread, I could make 8 sandwiches. Based on the cheese, I could make 5 sandwiches. And the reality is that I will never be able to make 8 sandwiches. I can only make the 5 sandwiches because I only have enough cheese to make the 5 sandwiches. So this becomes our theoretical yield. We'll talk more about that in a moment. And it's the cheese that is our limiting reactant because it generated the smaller amount of product. So the reactant that will generate the smaller amount of product is our limiting reactant. So that's the basic concept, and that's even some of the basic math that we're going to do. Again, we could have done this in our head. This is, by the way, this is limiting reactant calculation number 2. And when I'm doing limiting reactant calculations, I have to have a stoichiometry set up for each reagent. So I'm going to have a stoichiometry, as many stoichiometry setups as there are reactants or reagents. So that in mind, we're going to move on to an actual example of a chemical. All right, let's move on here. Answer some questions here. In the sandwich making process described above, what was the theoretical yield? The theoretical yield was the smaller of the 2 answers. The theoretical yield was 5 sandwiches. So 5 sandwiches. Okay. What was the limiting reactant? The limiting reactant was the reactant that gave us those 5 sandwiches. So it's the cheese. And how much of the excess reactant were left over? Well, how much of the excess reactant, what was the excess reactant? It was the bread. How much was left over? We could do some math and figure out how many slices of bread were needed to make 5 sandwiches. But I think in our heads we can do that math. To make 5 sandwiches, we needed 10 slices of bread. And so if we had 16 slices of bread minus the 10 needed to make those 5, we would have had 6 slices of bread left over. So all of this is just to emphasize that there is an excess reagent, and you will have excess reagent left over at the end because not all of it will be used. It is the limiting reactant that is completely used up. So the limiting reactant is completely used up by the process, The excess reactant, there's going to be some of that left over. And there's my little note. If you add some salt and pepper, then those sandwiches are going to be fantastic. So we're going to do a sample problem here. I'm going to work through it with you, at least get you set up here. So we have a sample problem B. It says if you react 3.4 grams of 2-propanol, now you're not familiar with that naming, but there's the formula for 2-propanol. You may be more familiar with it as isopropyl alcohol. 2-propanol, 3.4 grams of 2-propanol with 3.5 grams of oxygen gas. How many grams of water do you produce? And then they ask us which of these is the limiting reactant. So there are a couple of things that we need to notice. First of all, we have two reactants, and we are given reactant amounts. A reactant amount of the first reactant and a reactant amount of the second reactant. So now we can't just say, aha, one is in excess, so I'll just do one calculation. So now we're going to do a limiting reactant problem, which means that we're going to have to do separate calculations, limiting reactant calculations, based on each of the reactant amounts. It's asking us how many grams of water do I produce, and so I'm going to have water as a product out here. Let's go ahead and complete and balance this reaction. I know I have to have it completed and balanced so I can get my molar ratios. So this is a hydrocarbon reacting with oxygen. So we know that that is a combustion reaction. And in combustion reactions, I always have two products. My first product is CO2, carbon dioxide, and my second product is water, and it's probably going to be as a vapor, as a gas, because this is going to be burning, so the temperature is going to be fairly high. So those are my products. Let's balance it. 3 carbons, 1 carbon, so 3 carbons. 7 and 1 more is 8 hydrogens over here. 2 hydrogens and a 4 gives me 8 hydrogens over here. So 3 carbons, 3 carbons. 8 hydrogens on the reagent side, 8 hydrogens on the product side. And now I have 1, 2, 3 oxygens total on the reagent side, 3 of them. And over here I have 3 times 2 is 6, plus 4 more is 10. So 10 oxygens over here. So I have 3 oxygens over here, 10 oxygens over here, and you may recall that we have to put some fractional number here in order to make the 10 oxygens on the reagent side. Well, if I've got 1 oxygen there, I need 9 more here. So what times 2 gives me 9? It's 4.5. And now I have 1 and 9 more is 10 oxygens. Well, obviously I can't keep that decimal coefficient. So how do I get rid of decimal coefficients? I multiply it by 2. And if I multiply that coefficient by 2, I multiply all the coefficients by 2. So this one becomes a 1. 1 times 2 is 2. 4.5 times 2 is 9. 3 times 2 is 6. And 4 times 2 is 8. So now I have my completed balanced chemical reaction. And I'm just going to write up here what I have. I've been given 3.4 grams of the 2-propanol. So I'll just write that there to keep track of that. And 3.5 grams of oxygen gas. So I'll write that there. And it's asking me how many grams of water do I produce? So that's what I'm looking for, the grams of water. So let's work through this together. Step 1, we must write a completed and balanced chemical reaction or equation to represent the ratios of each reagent and product. And this will give us the ratios we can then use in our dimensional analysis. So that's what we've done there. We've done step 1. So step 2 says, then we must run a limiting reactant calculation test. And that's a fancy phrase for saying we do a dimensional analysis. We're going to do a calculation for how many sandwiches And by sandwiches, what do I mean here? I mean grams of water. That's what I'm looking for. That's what I'm trying to build, grams of water as a product that might be made by each of these two substances separately. So I'm going to have a limiting reactant calculation number 1 and a limiting reactant calculation number 2. Okay? And each of these limiting reactant calculations will be a dimensional analysis solving for the number of grams of water. So each of them will be giving me some number of grams of water. Okay? Whenever I do a limiting reactant problem, then my calculations have to end up at the same place so that I can compare them and then take the smaller of the two values. So the limiting reactant calculation 1 is going to start with my first reagent. So it's 3.4 grams of 2-propanol. So I'll start with that, 3.4 grams of 2-propanol. So I'll just abbreviate it 2P, 2-propanol. And I'm going to have a series of conversions that get me from grams of 2-propanol to moles of 2-propanol, moles of 2-propanol to moles of water, and then moles of water to grams of water. So I want grams of 2-propanol to moles of 2-propanol, and then moles of 2-propanol to moles of water, and then moles of water to grams of water. And that's a basic stoichiometry setup, and it's using dimensional analysis. So I'm going to convert from grams of 2-propanol to moles of 2-propanol, moles of 2-propanol to moles of water to grams of water. And then I have my grams of water based on the amount of 2-propanol reagent I was given. My next limiting reactant calculation is going to do the exact same thing, only I'm going to start with the other reagent. So basically I've tried to figure out how much water I can generate from one reagent. Then I'm going to figure out how much water I can generate from the other reagent. So it's like asking how many sandwiches can I make from the bread and how many sandwiches can I make from the cheese. So we're going to run each of these calculations separately. So here I have my second limiting reactant calculation, and here I'm going to start with a 3.5 grams of oxygen gas, and I'm going to convert first from grams of oxygen gas to moles of oxygen gas, and from moles of oxygen gas to moles of H2O, because that's where I'm headed. And then finally, I'm going to have moles of H2O to grams of H2O. Okay? And again, both of my limiting reactant calculations have to end up at the same place. I cannot compare them if they're not with the same units and the same substance. All right, let's plug in some numbers here. I know that molar masses are always for 1 mole, so I can plug in those ones right there. A mole, molar mass there, and a molar mass there, right? And now I have to figure out how many grams per mole, and grams per mole, and grams per mole, and grams per mole. Let's go ahead and plug in my molar ratios. Here's the heart of my stoichiometry. Moles of H2O, well, it's 8 moles of H2O for every 2 moles of 2-propanol. So we have 8 moles of H2O to 2 moles of 2-propanol. And for the bottom one down here, it's water to oxygen, so 8 moles of water to 9 moles of oxygen. 8 moles of water to 9 moles of oxygen. So now I have to do a little side calculation to calculate the molar masses of these substances. So I'm going to do that now. I'm going to do that on a little bit of scrap paper off on the side so that you don't have to watch me do my math. Okay, now that I've done that math, I can plug in my numbers. The molar mass of this 2-propanol, remember it's the mass per mole, not for 2 moles. So just because I have a 2 here in the coefficient doesn't mean I'm going to have 2 moles here. I'm just figuring out the molar mass, so it's always for 1 mole. And my calculations show, if I've done them correctly, 60.095 grams of 2-propanol for 1 mole. And then for water, it's 18.01 grams of water for 1 mole. For oxygen gas, O2, it is 32.00 grams for 1 mole of O2. Notice that it's 2 oxygens in that formula, so now I do have to have 2 oxygens in there. And for water, I know that's the same as up there, so it's 18.01. So now I have my numbers plugged in, and I'm going to do that math. And the answer for the top calculation, my first limiting reactant calculation, rounded to 2 sig figs, is going to be 4.1. And my answer for the bottom or second limiting reactant calculation from the other reagent, rounded to 2 sig figs, is 1.8. All right, so now that I have my answers for my 2 limiting reactant calculations, remember this is as if I had said how many sandwiches can I make from the bread, how many sandwiches can I make from the cheese, and then we take the smaller of the 2 numbers as the theoretical yield. So this smaller of the 2 numbers is my theoretical yield. What about this number up here? This never occurs because I don't have enough oxygen gas to react all the 2-propanol to make that happen. So let's fill in these gaps here in step 3. Once the calculations are performed, we take the smaller amount as the theoretical amount, that's this right here, the theoretical amount of our product that we could have created under ideal conditions. The reagent that provides this theoretical yield is this reagent right here, and we call that reagent the limiting reagent, or the limiting reactant. Remember, reagent and reactant mean the same thing. So limiting reagent and limiting reactant, they mean the same thing. What about this other reactant, the 2-propanol? Well, I had an excess of it compared to the oxygen. So it was the oxygen gas that limited me, and so this other reagent or reactant is said to be in excess. Okay? So that's how we work through a limiting reactant problem. So again, just reviewing. In the problem, we notice that it is talking about a chemical reaction, reacting reagents to produce a product. And then it gives us an amount stated for each reactant. So it's not telling us which one is in excess. It turns out that one of them is going to be in excess, but they haven't told us that up front. So to figure out which one is in excess and which one is the limiting reagent, we're going to have to do calculations on both to see which reagent gives us the smaller amount of product. In order to do that, of course, we need to go through the heart of the stoichiometry, which is the mole-to-mole ratio. Where do we get that? We have to complete and balance the chemical reaction so we get those ratios. So that's how we approach a limiting reactant problem. Set up a limiting reactant calculation for each reactant, starting with the amount of that reactant and ending up at the same place based on whatever you're asked for. It says how many grams of water do you produce? So that has to be where I'm headed for each of these limiting reactant problems. When I get the answers, I have to indicate that one of them is my answer, typically by circling that answer and putting a line through the other one that's not going to be true, because the one that is smallest is my theoretical yield and the other never occurs. So by circling it, I have completed the answer for this problem. If I don't circle it and if I just leave both answers there, I haven't really completed the problem because I haven't communicated which is my theoretical yield. So as the very last step, you need to circle your theoretical yield because that tells someone how much would you theoretically produce. Okay, so that's how we handle it. So now on the next page, I'm going to give you another sample problem and I'm going to let you work through it yourself. So here we go. We have an example problem here. Oh, and look at that. It is not a completed and balanced chemical reaction. It says, for this question, consider this single replacement reaction. So I've been told that it's a single replacement reaction. If 5 grams of copper metal are reacted with 5.0 grams of silver nitrate, how many grams of silver metal will be generated? And then they tell me that the copper is going to form a 2+ cation in aqueous solutions. So because this copper could be variably charged, I had to be told what the charge was going to be. So what I would like for you to do is I would like for you to attempt to complete this reaction, write the correct formulas of the products to complete it, then balance it, and keep in mind that the product here, the copper, is a +2 cation. Then balance it. And then once you've got a balanced chemical reaction, you're going to have to set up 2 stoichiometries. One starts with 5.0 grams of copper and solves for how many grams of silver metal would be generated. And your second limiting reactant calculation would start with 5.0 grams of silver nitrate and then would end up in the same place with how many grams of silver metal will be generated. And once you've got the 2 answers for your 2 limiting reactant calculations, we take the smaller of the answers, and that is our actual answer. That is our theoretical yield. Okay? So I'd like for you to give that a shot. I know that there's a lot going on there, but I think you can work through it. Give it a shot. Pause the video now. Work through it. And when you're done, you can restart the video and I will work through it for you. Okay, we're going to work through this problem. It's a stoichiometry problem. It's a limiting reactant problem because I've been given an amount of one reactant, an amount of another reactant, and asked how much product I can generate. So that's the clue that I'm working with a limiting reactant problem. To solve the limiting reactant problem, I'm going to need 2 limiting reactant calculations, 2 separate stoichiometry problems, each of which are going to try to figure out how many grams of silver I can generate. And since I'm doing stoichiometry problems, I know that I have to go through a mole-to-mole relationship somewhere in the dimensional analysis, because the mole-to-mole conversion step is the heart of a stoichiometry problem. And since I'm going to be going through a mole-to-mole conversion step, I have to have a balanced chemical reaction because that's where I get the molar ratios. Well, in order to be able to balance this reaction, I have to complete it first. So let's do that. It's a single replacement reaction. In a single replacement reaction, a single standalone element is going to react with the compound and kick out a species from that compound and take its place. The copper is a metal. It's going to kick out the other metal, the cation here, the silver. So the copper is going to come in and kick out the silver and take its place. What that means is that silver is going to be alone by itself, and it's a solid when it's in its elemental state. And the copper now pairs up with the nitrate. And I'm given this clue right here, so I know what the formula of the copper compound is going to be. It's a copper 2 nitrate. And since nitrate is a -1, I'm going to need 2 nitrates to balance that. And it's going to be aqueous. And there we go. I have my completed chemical reaction. Now I need to balance it. 1 copper, 1 copper, 1 silver, 1 silver, 1 nitrate, 2 nitrates. So I need 2 nitrates here. I've changed a coefficient, so I need to start over to make sure that I haven't messed anything else up. 1 copper, 1 copper, 2 silvers, 1 silver. Aha, need to fix that. Again, start over, 1 copper, 1 copper, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. And now I have a balanced chemical reaction. And that's good because I'm going to use that balanced chemical reaction. I'm going to use the molar ratios given by the coefficients. So first of all, I've got 5.0 grams of copper metal. I'm just going to put that up here just so that I can keep track of what I've got. Reacting with 5.0 grams of silver nitrate. So I have 5.0 grams of the silver nitrate. And I'm being asked for how many grams of the silver metal. So as I mentioned before, I'm going to need a limiting reactant calculation for every reagent. So I'm going to have a limiting reactant calculation 1 and a limiting reactant calculation 2. So the first one starts with the first reagent and its amount. So I've got 5.0 grams of copper, solid. And it is eventually going to give me some number of grams of silver, solid. So I'm going to have to set up a stoichiometry that will allow me to convert from that reagent to that product. The other limiting reactant calculation is going to start with the amount of the other reagent. So I've got 5.0 grams of silver nitrate. And it has to go to the exact same place, the exact same destination as the other calculation, because I have to compare them to each other. So grams of silver, solid metal. So again, notice that every one of my limiting reactant calculations has to end up at the exact same place so that I can compare these values and then take the smaller of the two values when I'm finished. So here I go. I'm going to set up, I need to go from grams of copper to grams of silver. I know that I cannot convert directly from grams of one substance to grams of the other substance. So I'm going to have to convert this first from grams of copper to moles of copper, then moles of copper to moles of silver, and then moles of silver to grams of silver. So here we go. I know that grams of copper are going to be in the denominator, so I can cancel them. And then moles of copper will be in the numerator. Then once these cancel out, I've got moles of copper in the numerator. That has to be in the denominator of the next step. And then I'm converting to moles of silver. Okay? And then the moles of copper will cancel out, leaving me with moles of silver. So I need one more conversion step. And I need to go from moles of silver to grams of silver. And we can see how these all cancel out. So the grams of copper cancel, the moles of copper cancel, and the moles of silver cancel. And I'm left with grams of silver. Now, in order to plug in the numbers, now that I have everything in the right place, I know that my molar mass conversions in my dimensional analyses are always for 1 mole. That's what molar mass means. It means the mass per mole, per 1 mole. And if I look at my periodic table, I see that the mass of copper is 63.546 grams per 1 mole. And if I look at silver, it is 107.87 grams of silver per 1 mole. Then here I have my mole to mole ratio that I'm going to get from my balanced chemical equation. 2 moles of silver to 1 mole of copper. And there we go. And if I've done my math carefully enough, my calculator tells me that the answer is 16.976, but I want to round it to 2 sig figs. So the answer here is 17 grams of silver. Now I'm not going to circle that answer just yet, because I don't know that that is my answer for the problem. It may be the answer for my problem, but I have to do the second limiting reactant calculation in order to determine which of these is the smaller value. Because the answer to this question, how many grams of silver metal will be generated, is the smaller of these 2 values. And I have seen many students on exams do the first stoichiometry and get an answer here and be so happy that they've got an answer that they forget that they have to do the other limiting reactant calculation. So we are not done yet. We have to do the other limiting reactant calculation. So setting up the other limiting reactant calculation, I'm going to convert from grams of silver nitrate to moles of silver nitrate. And then from moles of silver nitrate to moles of silver, because that's what I'm converting to, the substance. And then just as I did up here, I have to convert back out of moles into grams. Okay. So if I do my calculation to add up all of the masses of the silver and the nitrogen and the 3 oxygens, I will find that 1 mole of silver nitrate weighs 169.87 grams per 1 mole. And I already have this up here for silver. I can check that on my periodic table. 1 mole of silver, elemental silver metal is 107.87. And my mole-to-mole ratios I get from my balanced chemical equation, so it's 2 moles of silver to 2 moles of silver nitrate. So 169.87. So if I do my math carefully, then my calculator gives me several digits which I have to round to 2 sig figs, 3.17508, so I have to round that to 3.2. And now I am done with my math, but I am not done with the problem yet. Because the problem has asked me how many grams of silver metal will be generated. And I have 2 possible answers here, but only one of them is correct. So in order to signify which one is correct, I have to either circle the lowest one, or put a star by it, or say this is the theoretical yield, or some way signify that that is my answer. So it appears that when I have 5 grams of copper, I have enough copper to make 17 grams of silver. But when I have 5 grams of silver nitrate, I can only make 3.2 grams of silver. And so my silver nitrate is my limiting reactant. Silver nitrate is the limiting reactant, and the 3.2 grams is my theoretical yield. And the theoretical yield is how much I theoretically could generate given these amounts of my reactants. In fact, I am never going to get 17 grams of silver because I just don't have enough silver nitrate to do it. And there you go. That's an example of a limiting reactant problem. How did I know that it was going to be a limiting reactant problem? I was given an amount of one reagent and an amount of another reagent and asked how much product could I be generating. And that tells me that I'm going to have to run 2 stoichiometries, one based on one reactant and the other based on the other reactant. And each one will tell me how much that reactant could generate. How many sandwiches could I make from the bread? How many sandwiches could I make from the cheese? And then the smaller of those 2 answers is the correct answer. And the larger one never happens. Okay.